let's find where this function, this rational function, is discontinuous. By now you should know that a function will be discontinuous when the denominator is equal to 0. So what we're going to do is we'll factor the top and the denominator here. You get x, and plus 2, and plus 1. And in the denominator of x, and factors of 12 that add to 7 would be plus 3 and plus 4. This function is undefined when x equals -3 and when x equals -4, because that's when the denominator would equal 0. And what that means for the graph is you will have asymptotes, vertical asymptotes, which is an imaginary line. So at -3, and another one at -4. And as the graph is approaching, it's continuous everywhere else except for those two values of x. And so as the graph is approaching an asymptote, think of it kind of like a, like a little bug coming towards a wall, and it can't cross that wall. It has to either go up towards positive infinity and follow along that wall, or it would have to go down towards negative infinity. Those are the only two choices that the graph has when it approaches a vertical asymptote. And we'll look at how to determine if it goes to positive or negative infinity in a different video. For right now, we're just looking at where the vertical asymptotes occur. And so what you're going to do, to summarize that again, you're going to factor the numerator, factor the denominator, and when the denominator is equal to 0, the function is discontinuous. Notice that in this example, there's no matching factors in the numerator as there are in the denominator. I'll show you an example where there are matching factors in the numerator and denominator, and that's going to be something different than a vertical asymptote. So to find vertical asymptotes, you're going to find where the denominator equals 0. Blank page here. Okay, so to find your vertical asymptotes, you're going to want to make sure that you factor the numerator and the denominator. And before you look for vertical asymptotes, you need to simplify the function. So if there's any matching factors in the numerator and denominator, simplify those, cancel those out, and then take that result and determine from that point for which values of x the denominator is 0. And that's where your vertical asymptotes will occur. So let's look at another example here. Let's say I have something that's already factored. So if it's already factored, obviously you don't need to do that part. But let's say you have x plus 2 and x minus 5 in your numerator, and in the denominator you have x minus 1 and x plus 2. So this function is discontinuous at two values of x, at x equals 1 and at x equals -2, because the denominator will equal 0 at those two values of x. However, these are not both vertical asymptotes because we need to simplify the function first. So we get rid of the common factors of x plus 2 over x plus 2 equals 1. So we are left with x minus 5 over x minus 1. And our vertical asymptote, in this case we just have one, the vertical asymptote will be where the remaining simplified version of the function is equal to 0. So at x equals 1. So you would have a line, oops, make it a dotted line, and it's kind of a line that you're putting there to remind you it's not part of the graph, but it's going to be splitting the graph into two branches because you cannot have a point along that line. Now, something to point out here is we said that the denominator is equal to 0, not just at x equals 1, but also at x equals -2. So any matching factor that's in the numerator and denominator, it's still undefined here, but instead of a vertical asymptote, what you're going to have, notice how we removed that factor, which is a big clue as to how to determine if it's a vertical asymptote or a what's called a removable discontinuity. This is called a removable discontinuity. And it occurs where the denominator equals 0 and it had a matching factor in the numerator. So we were able to remove that factor and simplified it to this version, and so that's where you're going to take that result and find the vertical asymptote here. But the one that we removed, where it's undefined at x equals -2, that is a removable discontinuity. And instead of an asymptote, what's going to occur there is you're going to have one tiny little hole in the graph. I will show you another example. Oops, direction. Okay, so let's say you have a function like, let's go with like x squared minus 9 over x minus 3. So if I simplify, I'm going to factor the numerator, I'm going to factor the denominator, but we can simplify this function to x plus 3. However, the function is undefined and therefore discontinuous at x equals 3 because the denominator would equal 0 when x equals 3. So the function is going to look just like this. It's going to be the graph of f of x equals x plus 3, which hopefully you know that's a linear function with a y-intercept of 3 and a slope of 1. It's going to look just like this graph right here. Like the simplified version. However, at x equals 3, it's undefined. You can't have a point right there. So what that looks like graphically is you would have a tiny little hole in the graph. It's not an asymptote, just one tiny little hole, which I could fill in with one single point, and that is called a removable discontinuity. All right, so let's look at one more example here. So let's say I have f of x equals, I'm going to write it in factored form again, x minus 3, x plus 4, and I'm just making these up off the top of my head. And I have x minus 1 and x minus 3. The function is discontinuous at x equals 1 and at x equals 3, because the denominator is 0 there. We would have a vertical asymptote. I want you guys to pause the video and see if you can figure out where you'd have a vertical asymptote. And you will also have a removable discontinuity in this example. You won't always have both. You might have, some functions are continuous everywhere, but if you see that the denominator equals 0 at a particular value of x, what you're going to do to determine if it's a vertical asymptote or a removable discontinuity is you will determine where it's undefined, which we already decided x equals 1 and x equals 3, but if I remove that factor, because I can simplify that, I am left with x plus 4 over x minus 1. So we have a vertical asymptote where the simplified version is undefined, which is at x equals 1, because this denominator would be 0 at that value of x. We have a removable discontinuity at x equals 3. Okay.